I see everyone's getting logged in here and answering the questions. I appreciate your feedback. And I hope you're all doing well this afternoon, keeping warm if they're in a place that's colder than Florida. We do have a particularly nice day today. All right. We're just about finished here with the poll as everyone gets logged in. I'm sure there'll be some more attending later, and that's all right. But we got to keep to our schedule today. We've got a lot to get through, just a half hour to do it in. So I'm going to go ahead and close the poll now. So several owners, but a couple people looking to buy and a couple people interested in Bathy. So that's great. Great to have you all here today. So let me go ahead and get my screen share started. Welcome everyone to our first webinar here in the month of February, already the 18th, hard to believe. And we're moving right along with our topic this month, which is bathymetric systems. So today we're going to talk about and explore the overall field of LiDAR bathymetry and specifically focus on our workflow and some of the tools we have to help you deliver data to your clients. So my name is Joshua France. I'm the Mobile Division Manager here at RIEGL USA, and I'm coming to you live and in person from our new headquarters in Winter Garden, Florida. We remind you to keep an eye out for all of our exciting announcements here at RIEGL by joining our newsroom, which can be done on our website at riegl.com or rieglusa.com. This afternoon, right after this finishes at about 3 o'clock, along with the Mars landing, they'll also have the launch of our RIEGL cast series covering all things bathymetry as well, brought to you by Michael Sitar, our Airborne Division Manager. So please stay tuned for those exciting releases. All right, let's get underway. So this afternoon, we're going to cover the applications, a look at our bathymetric sensor offerings here at RIEGL, go into a little bit of mission planning and discovery about that, and then provide you with a detailed overview of how RIHydro gets the job done inside RI process. So for those of you who have not seen that yet, this will be a great first look at how easy it is to bring out the best data possible from our bathymetric systems using RIHydro. So why are we talking about bathymetry, you might ask yourself? Well, last year, the US Congress passed the Digital Coast Act, and it's providing more funding for more data collections. And if there's going to be more data collections, we need to provide you with more sensor options to collect the unique coastlines of the United States. As you can see from the map on the right there are a lot of unique coastline just in Florida, where a single standard flight line doesn't quite cover it or allow you to get an efficient coverage of some of the more difficult areas. So that's why we have some new system offerings to help cover that. So Digital Coast Act passed late last year in December. The Florida Coastal Mapping Project has been in the process of putting together user stakeholder data from all over the state of Florida. They divided it up into those 6 regions there, held meetings all across the state to get buy-in and to see exactly what needs to be done. The USGS led that effort, and they've been presenting those results at several different meetings this year. So I look forward to hearing more about that effort in the future from them. The Federal Geographic Data Committee has been tasked with looking into an open water initiative, and that doesn't stop just at the coastlines. It goes inland into our rivers and streams. Important information gathering is happening there. So bathymetry allows us to do and support all those initiatives through coastline mapping using shallow water bathymetry. We're very successful and confident in our ability to not just collect data near shore, but out further to the 20 to 30 foot marker. We can do that very reliably from our airborne sensors these days, which adds nice complements to some of the deeper channel systems out there, whether it's multi-beam sonar or other methods for collecting those types of depths. So this helps not only with our disaster planning, but also our response to it by knowing what the shoreline looked like before a hurricane decided to rearrange things. And there are many other topics and applications which is applicable, and these are just to name a few. So how do we go about capturing this information? Well, we offer two systems. We offer the VQ880G Mark II. This is a picture of our older initial system, the 880G, and we also have the VQ840G. As you can see, both systems are fairly easy and clean installations inside aircraft, and they are systems, like I mentioned. They hold both a sensor for the bathymetry part, the green laser channel. They have a camera or cameras, depending on your configuration of the 880G. And lastly, they have the integrated INS GPS system. So it's an all-in-one package. On the left side there is our new VQ840G, sensor mounted and ready to go on a helicopter mount. And that's sort of for the front of the helicopter. So it's got the top mount bracket there. And then you have the cables running, of course. So to talk a little bit further about the VQ840G and another installation angle here, this was done in a fixed wing aircraft to do some early tests here in Orlando with our partner GPI Geospatial was nice enough to fly that for us. So we have many different pulse rates. This goes to a maximum level of 200 kilohertz. And with this sensor, our main focus is flying low and slow. Its compact design does get us to that 33-pound weight, which is a little bit heavy still for small UAVs, but it is in that medium lift capability. And our Rycopter M can lift it for a period of time as well. So there are some UAVs out there where it is ready to go for, but mainly it's going to be a helicopter mounted solution, we feel, especially with a sweet spot of about 75 to 150 meters altitude for collection performance. This can be easily installed in a GSM mount. And like I mentioned before, not only could it have an integrated INS system, but you could also integrate it with a standalone system as well if you had that such desire. So the green laser is an elliptical scan pattern. This allows for a fixed angle of incidence to the water surface, enabling vertical target density, improved water surface penetration, and a more complete coverage of objects on the ground beneath and above the water surface. So this is really an ideally suited system for the complex coastline and inland water mapping. So you can terrain follow or route follow, as I would say. So moving into our larger system, the 880G Mark II. So we also have an 880G GH that allows for helicopter mounts. That's a smaller form factor, but has a bigger laser performance, as you can see here from the system. So this has both a IR and a green channel, so it's a dual wavelength system. The IR channel operates in much the same way most of our sensors do, in a scan pattern. So that's going back and forth scanning from a rotational mirror, and we're getting a scan line that scans across the face of the ground there, as you can see. Then we have our circular scan pattern of the green laser that's going in a circle, as you can see from the graphic on the left-hand side. It has a fully integrated 4-band camera solution available. This is either with the Phase 1 IXM 100 or 150 series, depending on your preference. And this produces a very small laser footprint, thanks to a low beam divergence from the laser, which really allows excellent multi-target capture capability, which is key for capturing texture-rich objects and complex objects on the ground. So the 880G has been around for a while, and the G2 as well. It's been very successfully used by some of our customers, including those that scanned the Florida Keys and the Florida Bay project. That was a NOAA project in the last couple of years. The Tampa Bay area has also been collected with the 880G Mark II, and all of Puerto Rico has been collected as well by several different RIEGL instruments, both in NOAA efforts to study the effects of Hurricane Maria. So let's talk about the mission specifications. So the VQ840G allows you to plan it in our standard planning application called RIEGL. The 880G Mark II is also available for flight planning capabilities. And what we're looking here is we're looking at what kind of point density will be produced, what's the safe altitude to operate at from an eye safety constraint, and some other factors. So let's start with the scanner settings. So this is all user input data. You can put in the terrain and look at that. So there's lots of complexity here to get involved with for sure. But just simply spoken, you can see that we have 5 kilohertz there. So that's right, it's a 5 kilohertz scan setting. Now, you're typically used to us talking about our 2 megahertz lasers, right? Or 2 million points, but this is 5,000 points. So this is on the lower end. That's right, because with this, the laser power is much higher at the slower pulse rates. The 880G Mark II has a mean power distribution across all of the pulse rates, so the performance isn't really changing in terms of its setting. In this case, it's very much changing by the change in the scanner pulse rate setting. So at a lower pulse rate, you're going to get better depth penetration performance through the water, and it'll allow you to get deeper in different types of water as well. So you can see here we control the scan rate, we're controlling the field of view, and of course we're also having the ability to adjust the laser beam divergence. And that's critical in making sure that we operate at a safe laser safety level or an eye safe level, excuse me. So if we then go over our point density, you can see that with a circular scan pattern, we get plenty of point density. It just isn't always where we would like it. It's on the edges. So in the middle is where our lowest number of points are, and that's at the 8.25 level here, as you can see. So those are the key ones, is the average and the minimum. And then we also are given details about that laser shot size on the ground based on our altitude and ranging performance. So the other thing that you have to consider with bathymetric data is you also have to take into account the timing. So we'd all love to be able to scan shoreline with bathymetric systems that looks like the picture on the right there from the Dry Tortugas. Beautiful crystal clear water. Our friends that collected the data for the Florida Keys know that that's a great time to collect data is in that area. However, that's not always the case. Sudden changes in the natural habitat, the environment can affect an algae bloom, as you can see here, that happened in Lake Erie. So timing is very critical for getting the bathymetric data to collect just right. So that's a little bit about the mission planning and the acquisition parameters that you have control over. So then after you're all done, we get to go into RIEGL. And I've recorded a quick video for everybody to watch about RIEGL and how it collects data. Sorry, not collects data, but processes data. So I'll be now showing you this video from my screen capture of RIEGL. This is after the data has already been processed. We'll take a quick look at it, and then we'll go right into the tools for RIEGL. So here we go.
Thank you for that great introduction. So today we're going to go a little bit deeper into the point cloud and analyze some of the features of RIEGL and the tools RIEGL in more detail. So we have here an 840G project. We've already processed it as you would any other laser data project, whether it's topographic or bathymetric. The same steps have to be followed. You run the data processing ledger and you create a 3D point cloud. Let's take a quick look at the point cloud here. So I'll just throw in a couple of lines here. Just these 4 right here. You can see it centers in on the project. You can zoom in, and you can see we have a little town with some buildings there. Zoom in the 3D here. Make my point size a bit smaller. And you can see we have a sort of a harbor area. This is a Crystal River area. This data was collected in connection with GPI, Geospatial. They flew this for us in their aircraft. So it's a little bit higher altitude than the 840G, but it performed quite admirably in the situations. We can see some pools in there as well as some nice areas. So we'll be able to get to work here. So As with all things bathy, our objective was to penetrate through the water surface and get ground points. So it's very hard to see from this initial cross-section or section of the data how well we did. So we can take a quick slice here. And we can see that a couple of things are true. So we got some noise in there, and we got some strata in here. So you can see here we have, the top layer is likely the water. We got some water column filter objects to filter out, and then we have bottom. Okay, so it's an overall very typical example for a bathymetric project. So you're going to hit targets both on the top of the surface, in the water itself, and then on the bottom, just like in a forest vegetation scenario. So let's walk through some of the tools that we use to help us classify and create data ready for use for running ultimately the reflection tool. So we have to fix the refraction, So the refraction, of course, is taking that property right from your physics book of Snell's law and applying it. Now, it's easier said than done, of course, because in real life we don't always know the exact surface angle. It's not a flat plane, water is not static, it's very dynamic. So there's a lot of things to take into consideration. So we need to create a water surface model. Well, to create a water surface model, we have to classify, you guessed it, the water surface. So let's go ahead and look at creating the water surface model. So we go up to our toolbar here, and we drop down, and you can see RIEGL is available. Now, I will say that RIEGL is only available if you have the RIEGL installer. So if you have regular RIProcess 1.8.7, you're not going to necessarily have access to the RIEGL toolset. As obvious as it is, this is only available if you have bathymetric data. So we're coming in, we're going to classify the water surface points first. Okay, so we have this nice little wizard here, and we're just going to do a couple of lines sampling. Okay, so we're just going to do the same 3 lines that we just pulled in. And we have different settings that we can use. So I'm going to go ahead and select this 840G setting that I created, but let's take a look at what it means. So our target class is set up. We have a green laser only in this scenario, as the 840G that we use has a 12 megapixel camera along with the green channel. There is a version of the 840G that also would include a single point rangefinder in the IR channel to help with water surface classification. All right, and so we can pick our cell size. So the cell size is how small of a cell it looks at. And the smallest cell size that we're going to use here is about 1 meter. That's about the reasonable small size you can really fit to classify water in some of these areas. So we're going to go ahead and select OK. Then we're going to have each of these records, we have options to how to process them. So we can process them all in one giant lump sum. We can process each record separately. That has more to do with when you have the 880G with 2 channels, as we do a forward channel 0 and a backwards looking channel 1. But in this case, we have just 1 channel. So we're going to let it process. We're going to use all of the data sources to look at it. We want it to look at everything. We don't want it to avoid anything. Now, obviously, we can say for sure that the isolated points should not be used and looked at. And we know that some of these other points, like the RIMTA unresolved points, are probably also not water surface points in this example. And we don't really have anything else classified. Click OK. And away it goes. So you say, okay, it's not doing anything. Great, I knew it. But we pull up our task servers, we can see this is running pretty quickly here in the background. All right, so now you can see we have our water surface model successfully finished. Let's go take a look at this. Sorry, too many views. We'll start here with a brand new view to make things easy. We're just going to look at record 7. Keep life simple, folks. Always better to keep it simple. All right, we'll just start in here. I'll go ahead and, again, use the point rules here to create point rules for the scans. This just gives us a quick idea of all the things in there. So we have our water surface points. We've got a 3D here. And the gray areas are where it's been classified, which you can see right in there. It's picking up quite a bit of surface area there. So there's some, some shallow water in here, so it's a little mixed. But for the most part there, let me just turn off those ones there. So there's our patches. So it did a pretty good job of finding it. So now let's go ahead and use those classified water surface models to actually create a water surface model. So again, we go to Right Hydro, water surface model. Go to record 7 here, just to take a look at one. Again, we're using a river, we're using a smaller cell size here to help us find some of those granular details along the shore so we don't pick up docks and other things. We'll go ahead and start that right off. All right, so there we go. It's a pretty quick model. It's not, it's just calculating that. It's using the data we already have there. It's interpolating it, pulling it out, and we are done. All right, another successful model created. So now we'll go back to view 5 there. Open that up. Toss in the water surface model. All right. There it is. Pulls in really nicely. Even pulls down into that canal just about. Covers a little bit more area, but that's the general water surface area there. There we go. Takes a second to load sometimes. We have pretty good coverage there for the most part. So right along the water surface, just like we'd expect. All right, so now that we have that water surface model, we can actually start the next tool, which is to execute refraction correction. So again, we're going to use, here it shows us the list of the ones that have it and the ones that don't. Just need to count down here. Which record are we looking at here? There we go, 193855. So it's going to look at all these point settings here. Okay. And what we want it to do is we want it to look at those records and we want it to put it in the water class. All right, or the, sorry, actually I want them in the underwater class there. Highlight all these, we want to run all of it. There we go, we want to look at everything, not the MTA points, of course. And look at the water surface, we don't need it to use that class. All right, so we're ready to go there. And then we get into some more technical parts here, which is to have a look at the depth bias correction, refraction correction. So we pull up this calculator here to see what we're at. And these are some defaults here. So we're saying we need to come up with the water temperature. Now this is very warm water. It's just natural spread spring. So we're closer to about 22. It has a very low salinity. So we're going to make that as low as possible here. And we're dealing with a 532 wavelength. It's of course the wavelength of the green laser. All right, so it calculates that for us. And we're ready to go. So we have our refraction index of the water and our depth bias correction. So now we're going to apply that to the data. And it's just going to be adjusting those points that fall underneath the water surface to adjust the bottom. So as you can see here, we have a pretty advanced set of tools for Right Hydro. You can also have some other options to bring in other water surface models that you can create on your own and bring them in, or use some third-party software and bring those in as well. And everything comes right into our process and it quickly runs through it. The one tool that we haven't showed yet is we haven't talked about the water column filter, which also can be used as well. So let's go back in here real quick, and let's again go to our laser data and have it create point rules from scans. We'll go ahead and turn off our water surface model because it's a little bit big. And let's see all the point rules we've popped up. So again, we don't need to see that, but we want to see the underwater points and those. Let's take a look out here, different area, just to show you that the whole data set's looking at it. And you can see the gray is the water surface, and below that is the underwater surface. So if I turn off the water surface here, oh, I need to hide it. You can see all the points on the bottom of the water are in purple. So you can see there's sort of like a fish hook pattern right there that you can see through the water. And so that those are underwater points there. There's something in the water there. So if we actually go and look at the images for that same area from our 12 megapixel camera here, you can see there's that exact figure in the photo. Side-by-side comparison, yep, it's exactly what it looks like. So some good bottom detection there. There's a few points that are missing in this area, but you can see it gets a little bit deeper there. There could be some vegetation growing in there, some shadowing area, so it's a little bit darker of a bottom in there, so not quite able to capture all the way through that. That's an area where it's using some waveform stacking or averaging can be utilized in the future. Thank you for watching. Please email me with any questions about RIEGL or.
All right. So sorry to cut myself off there. That trigger control is a little bit faster than I expected. But I think you get the idea that RIEGL is a well-tuned machine ready to go to work to adjust your data and complete the process for bathymetric data acquisition and post-processing. So we'll close out with a quick poll question here. Thank you all for tuning in today. And while we look at this, also feel free to type in the questions box, any questions that you might have for me, and we'll do our best to answer those live here on air. All right, so as this is coming in, one of the first questions is what's the main driver of depth performance of the 840G? Well, that's a great question. So the main driver of that happens to be the receiver field of view in combination with the pulse repetition rate. So the lower pulse repetition rate and then a wider field of review from the receiver will enable you to get the absolute maximum depth penetration information from that water body. Of course, that assumes a lot of things line up and go right for you in terms of the water clarity. And of course, by having a wider field of view, you also can pick up some more background radiation and things that you may not be looking for in your data set, to say the least. All right, so thanks for all voting in our poll. Well, a lot of interest in becoming data collectors someday. That's fantastic. All right, so we're all done with the formal part of the presentation. So again, if you have any questions, now is that time. I thank you for your attention today. Getting you finished just on time as promised, just 2 minutes shy of 2:30 in the afternoon here in Orlando, Florida. So feel free to ask questions, and of course, email us at info@regelusa.com would be the easy one, or you can use my email address, which is jfrance@regelusa.com. So any questions? Okay, so the first question we have is related to the 880G Mark II with its 2 different wavelengths or bands. So the IR channel on the 880G helps us classify the water surface. So where we get water pickups from a 1064 laser, we're able to get just the top surface there, which allows us to better classify the water. Because sometimes with the green laser, we get the water surface and sometimes we just miss it. So that's one of the primary reasons for having the IR channel there. Another question about vibration isolation for the LiDAR. So of course, with a tightly coupled system, we always try to mount everything in a tight, compact format, so that way the LiDAR sensor is in line with the IMU for vibration sensing and movement analysis. And then typically most of our mounts have some shock absorbers in it to keep the aircraft vibrations out of it. All right, well, if I didn't get to your question, I do apologize, but we're at our time here. Some of them might be a little bit more challenging to answer on air, so we'll get back to you shortly. And I appreciate everyone's time and attention this afternoon. One final one that I can toss a fairly simple answer to is, well, caveated answer is, what's the maximum depth in meters that the green laser 840G can penetrate? Well, we've consistently proven a 4-meter depth penetration when our testing so far. We haven't used it in enough variety of situations to have a maximum number yet. What we've just been able to successfully always capture consistently across the full pond or stream area at least 4 meters every time out. So that's a very repeatable performance. It can go down to a 2.5 secchi depths, which gets into some more nuances related to the water turbidity and so on. So it's a half answer. But anyways, thank you all very much, and see you next time.